Hello everyone, and thank you for joining us today. Welcome to ABO's webinar series. Today's topic is Protective Relay and the Power Delivery System, how it all fits together. My name is Ron Spatero, and I'm the Marketing Manager for ABO Training Institute. I'll be your moderator for today's presentation and supporting you on technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will answer your questions during our Q&A segment at the end of the webinar. All attendees will receive one professional development hour and one NETA CTD for attending. You will receive your attendance confirmation in an email within 2 business days after the webinar. This email will also include a copy of the PowerPoint presentation and a link to the recorded video of the webinar if you'd like to watch it again or share it with colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered after the webinar ends. Our presenter today is Dennis Moon, Senior Relay Instructor and Curriculum Advisor for ABO Training. Okay, let's go ahead and get started. Thank you for joining us today, Dennis.
Thank you. Hello, everyone, and welcome. We're going to discuss today protective relays in the power delivery system and how protective relays fit in the power delivery system as far as making everything work together. In order to do that, we're going to first talk about some power delivery system fundamentals. So here's some concepts about components of the power delivery system that we kind of need to be familiar with. Number one, we need to be familiar with the generation component of the power delivery system. 2, we have step-up transformation. We're going to change the generation voltage through transformation to a transmission voltage. Then we're going to transmit. Then we're going to do step-down transformation and step that transmission voltage down to a distribution feeder level, and eventually we're going to get the power that we're trying to deliver to our load. Now, these are only concepts. They require physical system devices. So let's take a look at what these physical devices are in the power system, power delivery system. So first of all, we have an energy source. Now, I've been kind of facetious here and put some Red Bull and Mountain Dew and other things that might be energy sources, but really what we're talking about is things like wind power, we're talking about solar, we're talking about coal, we're talking about nuclear, we're talking about water, we're talking about gas, and there may be other energy sources. These energy sources, with the exception of solar, are used to turn a physical electrical generator. That generator is going to produce the quantities necessary to eventually get power to our loads. So we have the energy source, we have the electrical generator, then we're going to step up that generator voltage to a high voltage through a generator step-up transformer. Then we're going to transmit that high voltage across transmission lines. Then we're going to take that high voltage into a substation that's going to again transform, as we mentioned earlier, high voltage to medium voltage and medium voltage to low voltage. And from there, we're going to distribute that power to our electrical power loads. And our electrical power loads, as an example, are our residents, where we live, industrial facilities, businesses, heavy industrial, There are all sorts of load centers that we're delivering that power to. What exactly, now that we've talked about the power delivery system, physical devices, what are we actually delivering? So let's take a look at that and see what's being delivered. All right, from that generator, we are getting current, voltage, frequency, watts, and if necessary, VARs, volt amp reactance. If the current and voltage are in phase with each other, we're delivering watts. If we have a phase angle displacement between current and voltage, we're delivering watts and VARs. When we have this phase angle displacement, and we're talking about a phase angle between, as an example, the A phase voltage and the A phase current, then three quantities come into play. We now have volt amps, which are going to be greater than watts, and we're going to have volt amps reactance as part of the power being delivered to our load. Note that we have a three-phase sinusoidal system that you can see on the right of the slide here, and that three-phase system delivers voltage and current at the designated frequency of the power delivery system, which in our case is 60 hertz, meaning that there are 60 cycles per second of power delivered to the load. Now, if we're delivering current, voltage, frequency, watts, and VARs, those inputs into the load have to have operating parameters. So let's take a look and see what the operating parameters are for the various physical components in our power delivery system. So take a look at this. Each physical component of the power delivery system has operating parameters. Generators and transformers have a maximum acceptable volt amp rating. So we're going to ask the question, hey, what happens when we exceed that volt amp rating? Transmission lines have current carrying limitations based on line impedance. What happens when we exceed those current carrying capabilities? Distribution and feeder buses have maximum acceptable ampacity ratings. What happens when we go beyond that? Loads generally have maximum current ratings for safe operation. What happens when we exceed those safe operating levels? In order to fully understand the power delivery system, I want to take a bird's eye view here of that power delivery system. So take a look at this. Here's a bird's eye view of the power delivery systems that are available to us in the United States. So as an example, note here that we have three power grids. Now within each one of those grids, power delivery systems aren't independent of each other. So as an example, in the eastern grid, we can have many power delivery systems, but they're all intertied together and they're not independent of each other. Now, we have three major bulk power grids in the U.S. Most of the power delivery systems are all tied together in one of these three major grids. So let me give you an example. If I was an electron being produced by a generator in North Dakota, I should be able to travel all the way to the southern tip of Florida on A phase, because all of the A phases in the bulk power grid are tied together. All the B phases are tied together, and all the C phases are tied together. So we can have numerous power delivery systems within the bulk power grid. They're all tied together and capable of delivering the power that we need to any load. Now you'll notice, just as a side note here, that I have the eastern grid, the western grid, and what we'll call the Texas grid, or ERCOT, the Electrical Reliability Council of Texas. Note that there are no AC ties between the grids, but there are DC ties. Now, these three grids have advantages and disadvantages. Let's take a look at some of the grid advantages and disadvantages. First of all, the advantages. When I have a bulk power grid, I'm able to have on the entire grid and across all of my power delivery systems reasonable voltage and frequency. So as an example, sitting here in this room, if I was to plug in my Fluke and look at the frequency, I'd find the frequency to be probably 60.001 hertz. And my voltage would probably fall between 115 and 125 volts AC. And that would be true across the vast majority of the bulk power system. Second of all, one of the next advantages is a spinning reserve that's available for planned and unplanned outages. Now, what that means is I can plan to take my generating plant out of service, and that doesn't mean that my customers are going to go without electricity, because the grid has spinning reserve that can take up the slack for a lost power plant and continue to provide voltage, frequency, and the load values necessary to keep the power delivery system up and running. So whether it's a planned outage or an unplanned outage, the grid can provide the necessary voltage, current, and frequency to service all loads. Third, generating stations don't need to be near the load. As an example, we're here in the Dallas-Fort Worth area. Large metropolitan load center. The generating stations are miles and miles away from the Dallas-Fort Worth area, and yet the grid is able to supply all the voltage and current necessary to service this large metropolitan load. Fourth, the grid is highly efficient due to frequency synchronism. And what that means is all of our generators are synchronized together at 60 hertz. And so we don't get frequency fluctuations, therefore we don't get angle fluctuations, and the system is highly efficient because every single generator is synchronized at 60 cycles. All right, that's the advantages. But if there's advantages, then we need to look at the disadvantages. And some of the disadvantages are that if I have a large system disturbance, then it can affect large portions of the grid. The 2004 outage in the Northeast is a good example. Differing engineering philosophies can cause design and application problems. We don't all buy exactly the same equipment. We didn't all graduate from the same engineering school. We don't all have the same system design philosophies. So these present problems to us that have to be overcome by the grid operators. Third, grid infrastructure is aging at different rates, so all of the maintenance programs aren't all identical. We don't maintain our transformers, generators, circuit breakers at the same rate or do the same maintenance procedures on them. So those can be disadvantages to keeping the grid up and running all the time. And furthermore, with the advent of solar and wind power, some power users are defecting from the grid. They just disconnect. You've heard the term off the grid. That's happening with some of our power users. A further problem with that is that some of our power users go on and off as their needs dictate, causing problems for grid operators. All right, now what we've done is we've talked about the philosophy behind power delivery systems. We've talked about the physical devices that are necessary. We've talked about the grids in which most power delivery systems are maintained. So now let's talk about our protective relays. Why are they necessary in this power delivery system? Well, first of all, let's answer some interesting questions. Protective relays would not be needed in power delivery systems if the following was true. If system voltage, current, and frequency always stayed within operating parameters. 2, if none of the physical devices ever aged or wore out, we wouldn't need protective relays. If Mother Nature could be 100% controlled by us so that there weren't any tornadoes, hurricanes, windstorms, lightning strikes, earthquakes, floods, ice storms, or any other natural disasters? And how about controlling animals of all types and preventing them from having any interaction with the power delivery system? If those things were true, no need for protective relays. What if we could totally eliminate human error? We wouldn't need protective relays. Or what if science discovered a way to live without electricity? Hey, no need for protective relays. However, experience with the power delivery system has shown that abnormal system conditions occur frequently on the power system. In fact, I guarantee you that right now, somewhere in the three grids, Western, Eastern, or ERCOT, there's some kind of power system disruption. It happens all the time. These disruptions are commonly called faults. They're abnormal system conditions, and they cause damage or disruption ranging from relatively minor problems to catastrophic loss of life and infrastructure. Causes of faults can be, again, acts of nature, accidents caused by people, equipment, animals, and equipment failures. So let me just show you a couple of pictures of the results of faults. So here we go. Here's a relatively minor fault. You can see that we've had arcing across the bus. There wasn't an outage in this case, but it's going to have to be repaired at some point, considered to be minor. Here's a relatively major fault. Notice in the left-hand picture, all three buses, A, B, and C, are burned in too. This is going to be a long outage, weeks, perhaps months. And notice the switchgear on the right. At least two pieces of switchgear have been destroyed here. They have to be replaced, and that's going to take time and effort to do that, and maybe a prolonged outage. All right, here's catastrophic faults. On the left, you can see large power transformers completely destroyed by a fault. And on the right, you can see a generating station that has lost its generator step-up transformer and required months of outage time. So that's what our faults do, and that's what our relays have to be able to detect and take control of. Let's take a look at the types of faults. We know what they do now and what they can cause. Let's take a look at the types. So here we go. There's four types: three-phase faults, three-phase to ground faults. This would be where the lineman left the grounding chains on and we close the circuit breaker. And our protective devices have got to be able to catch that instantaneously and remove the fault current that would be generated. We have phase-to-phase faults. I had a student the other day from India that said snakes across the phases are a big problem over there, as those snakes crawl up onto the switchgear and circuit breaker bushings trying to get birds' nests. Head on A phase, tail on B phase, guess what? Phase-to-phase fault. Next, we have phase to ground faults, by far the most common faults in the United States. Most are lightning caused. Then phase to ground faults. Now be aware that a phase to ground fault can evolve to a phase to phase ground, or vice versa. A phase to phase fault can evolve from phase to phase to phase to phase to ground. In any case, if any of those four types of faults occur, then interesting things happen in the power delivery system. So let's ask the question, well, what happens during one of these faults? So here we go. First of all, we get significant current rise and or a voltage drop that results in large mechanical stresses caused by big magnetic flux fields. The higher the current, the larger the magnetic flux field and the more damage that flux field can do. We get thermal or heat stress. Reactive current will flow on the power system and cause system disruption. We get possible negative sequence currents if it's an unbalanced fault, and most faults are unbalanced, so we can almost guarantee you that we're going to get negative sequence currents. We're going to get possible zero sequence currents flowing in the neutral and ground conductors of the power delivery system, plus arc, blast, and burn functions. Now, look what happens when we have a significant rise in current. Some bus faults may exceed 200,000 amps, depending on the available source current. There's very few devices in the power delivery system that can withstand that kind of current for very long. This high current will cause severe thermal damage to power system components and will last until we get the following. Phase separation, that's not good. That means the conductor is burned in too. Circuit breaker operation, yeah, that's us. That's what we want to happen from the protective relay end. Or we can lose the source. We don't want to do that unless we absolutely have to. As an example, we may have to shut the generator off even though the generator is faulted because it's feeding fault current to a remote fault. Or we might have to shut the transformer down because it's feeding fault current to a remote fault even though the transformer itself is not faulted. We might have to do that. We hope we don't, because our relaying is done properly. All right, so that's what happens with a significant rise in current. Next, we have a drop in voltage. Now think about this. If the voltage drops and the load is fixed, the current must rise. That's Ohm's law. So here's the situation that we face. Even if a power delivery system isn't involved in the fault, if it sees a voltage drop, the current in that unfaulted power delivery system is going to rise. Furthermore, the drop in voltage causes undervoltage conditions and in part due to higher fault current, and system stability may become an issue. So we're concerned about the voltage drop as well as the current rise. All right, along with the voltage drop and the current rise, we already mentioned that we get mechanical stress due to the heavy magnetic flux field caused by the high current. And this heavy magnetic flux causes severe stress on all the welded and bolted and anchored components in the power system. The stress may not be observable, but it's still there. This is the reason we do thermography as an example, so we can see if our welds and bolts and anchored components are in good operating condition and not overheating. So high torque on metal components caused by heavy flux may cause actually more damage than the arc, blast, and burn generally associated with fault current. We saw the other day as an example where the winding of a transformer was twisted off its pedestal due to the high magnetic flux fields created under internal fault conditions. All right, so we talked about high current, voltage drop, mechanical stress. What are some other fault conditions that occur in one of our four faults? We may have reactive current flow causing system disruption. And when we talk about reactive current flow, we're simply saying that there's a phase angle difference that is created between volts and amps. We may get negative sequence currents that appear on the system, and those negative sequence currents cause damage to the rotor of our generators and motors. Furthermore, we'll get arc, blast, and burn functions. So those are some, not all certainly, but some of the results of fault conditions on the power system. All right, now we see what happens on the power system. Now, what does the protective relay have to do with those things that happen? So take a look at this. The purpose of the protective relay is, one, to protect every device in the power delivery system. We can't leave anything out because all of the components are subject to high current. Next, our protective relay has to be selective so that the circuit breaker, the device closest to the fault, operates first. If that circuit breaker fails to operate, then the next upstream device has got to operate. So what we don't want to have happen is our transformer to trip offline because we have a fault 7 breakers away. So we've got to be very selective. Third of all, we've got to provide system protection while allowing normal system operation. All right, our protective relays are generally placed in protective zones. So here we're going to show you some possible protective zones. There's a generator zone, there's a low voltage switchgear zone, a transformer zone, a high voltage switchgear zone, transmission line zone, another high voltage switchgear zone that's again going to then go to a transformer zone, and we're going to knock that high voltage back down to usable distribution voltages. Each zone will have its own dedicated relays and circuit breakers, but zones overlap so we can have complete protection coverage of the power delivery system. All right, let's see how it works. So take a look at this feeder bus. Notice that we have two parallel transformers. They're circled in black. We have 4 loads. You can see those loads labeled. And we have 3 tie buses circled in red. All right, now here's a fault that occurs on the load side of feeder breaker 52-1. Got the arrow pointing left there where you can see where it says fault with the X. Okay, so here's what happens under this fault condition. Transformers feed fault current to the fault. The relay 50/51 on the load side of breaker 52-1 detects the fault. That relay sees that fault. If the fault current exceeds the relay setting, the relay will trip breaker 52-1 and remove the fault from the power system. Now think about this. All other unfaulted loads remain intact with minimal disruption to the system. So here's a summary of what we just talked about. The fault occurs, number 1. 2, the relay detects the fault. 3, the breaker opens. We do lose that load, but the other 3 loads remain intact. So we have minimized the amount of disruption by our protective relays doing their job. Now, let's look at a bus tie fault. Here's our bus tie. We've got it encapsulated in a red box. So note that we have a fault between breakers 52-I and 52-8 with associated relays 67-I and 67-8. Now these 2 relays have to be a little bit more sophisticated because they not only have to detect magnitude of the fault current, but they've got to be able to tell direction of the fault current. So if the magnitude and the direction are correct, then 67-1 relay, or excuse me, 67-I relay and 67-8 relay will issue a trip signal to 52-I and 52-8, opening both circuit breakers. Note then that all loads remain intact and there is minimal system disruption. So here's a summary now of what we just talked about. Notice that our red arrow is pointing to the fault. Blue arrows pointing to the relays that are detecting not only fault magnitude but fault direction, and our green arrows pointing to the breakers that will open up when they receive a signal from the relays. Notice that all the loads remain in service and we have very little, if any, service disruption. That's the way we'd like our protective relays to operate in the power delivery system. All right, so here are the necessary items that are always present in the power delivery system if we're going to protect it. So take a look at this. In order to protect any component of the power delivery system, the following devices must be present. 1, got to have a protective relay. 2, I've got to have current transformers and or voltage transformers to give the inputs into the back of the relay. And 3, circuit interrupting devices such as circuit breakers, circuit switchers, vacuum breakers. There's a whole list of things that have to be able to interrupt fault current flow into the protected equipment. So in the case of this relay, you can see 3 CTs on A phase, B phase, and C phase feeding into the relay plus ground. Then you have 3 voltage transformer inputs into the relay. If the current and or voltage exceeds the settings of the relay, then the relay will issue a trip signal to the circuit breakers. Now those could be 3 independent circuit breakers, or they could be a 3-phase circuit breaker with all of the circuit breaker poles contained in one device. In any case, when we see current and or voltage above setting, then the relay will issue a trip signal to the circuit breaker, and the circuit breaker will interrupt any fault current flowing into the protected equipment. All right, now, what types of protective relay are out there? In other words, we've got this blue box that we see in our little drawing. What types of protective relays does that represent? So here we go. We have generally 3 types. We have mechanical protective relays that operate on magnetic principle. We have solid state devices that use discrete components. Now, think about this. When we say solid state, what we mean is we're taking an analog AC signal and we're converting that to a DC signal that represents the AC signal, so that all of the measurement and all of the settings are done by discrete electronic components rather than by AC actuated components. Then third, we have numerical or microprocessor-based relays that directly convert the analog AC signal into a direct digital signal, or in other words, ones and zeros. All right, now that we know the types of protective relays, we're going to discover right now that all protective relays have some common traits that are necessary for them to operate. So take a look at this. Relay inputs come from current transformers called CTs and potential transformers called PTs, or voltage transformers. Now, these CTs and PTs are necessary so that we can reduce primary current and voltage, which can be in the thousands of amps and hundreds of thousands of volts, to secondary voltages and current that are proportional to primary, but that are safe. So all of our CTs and PTs use a ratioed value of primary to secondary so that we can have inputs into the back of the relay can that rarely exceed, under normal circumstances, 120 volts and 5 amps. So notice that the 2 items on the left are CTs, 2 items on the right are PTs, and those will be familiar to you as you work in the power system. All right, so we've got CTs and PTs. Now the next thing of interest is that all of our relays have settings. So notice that the BDD mechanical relay on the left-hand side has settings taps that directly influence the AC inputs into the relay. The middle relay, our solid state device, has taps also, but those taps control the DC portion or discrete component portion of the relay. The third type is our microprocessor-based or numeric relay settings, where we simply imprint the numeric value for the setting on the microprocessor chip itself, and the relay determines from the microprocessor, ones and zeros, whether or not settings have been exceeded and whether or not a trip should be issued. All right, so far we know we've got CTs, PTs, we have settings. Then the third thing that all relays have in common is a trip circuit. So notice in this drawing that in our case, we have a relay contact that will close if we exceed settings, If the circuit breaker is closed, indicated by a closed 52A contact, then we'll apply DC to the circuit breaker trip coil, and the circuit breaker will open, causing the fault current or other disturbance to be removed from the power system. So, again, in summary, CTs and PTs, settings, and a trip circuit. All right, now let's look at a couple of simple operating principles for a couple of our relays that we see out in the power system. First of all, let's look at the most standard and most common relay in the power system. That's our overcurrent relay. Here's the operating principles. First of all, we'll have instantaneous overcurrent operating, which is a 50 device by IEEE designation. Its setting comes from short circuit analysis, and it operates in 3 cycles or less. In other words, no intentional time delay. It's instantaneous operating. Okay? We also have another type of overcurrent relay called the time overcurrent relay. Its designation is number 51, and it's set as per a coordination study and uses various inverse time curves. Now, by inverse, we simply mean that the higher the current, the faster the relay operates. So the graph that you see on the left-hand side here is a mechanical relay time curve. It's inverse. The middle one is a solid state time curve, but notice it's also inverse in principle. And then the one on the right is a numeric or microprocessor-based relay, and it's an inverse curve. So again, the principle here is for 50 instantaneous operation, for 51 inverse time overcurrent operation. By the way, just a note, the instantaneous would always be set higher than the time overcurrent function. All right, let's look at another type of relay operating principle. That's the differential operating principle. Note that what the differential operating principle does is it compares currents on each side of the protected device. So as an example, in the generator protection zone, we look at the neutral current of the generator and the load current, and we compare the two. They should be identical. If there's a difference between the two, something's wrong. And if that difference exceeds differential setting, then we're going to trip the generator breaker. Notice the bus differential zone of protection. If I have 1,000 amps going into 52M, then 52-1 and 52-2 had better account for 1,000 amps. Otherwise, there's a difference. And if that difference exceeds the setting of the bus differential relay, it's going to trip. The third type of differential principle is the transformer differential, and we simply say that the current on the high voltage side and the current on the low voltage side of the transformer have to match by ratio. If we don't match by ratio, there's something wrong, and we're going to trip the associated circuit breakers. All right, here's a couple of more differential operating principles that are very interesting. Notice we've already said if the different currents exceed setting, then we're going to cause relay operation. However, with differential relay, the differential relay has to be able to differentiate between inrush current and fault current. It has to know what the difference is. Furthermore, if we're passing fault current through the protective zone, we don't want to trip, and our relay has to know whether we've got through current or whether we have an internal fault. If it's in zone, we want to trip instantaneously. If it's a through fault, we don't want to trip. So what we're saying here, very simply, is the fact that this relay has to be able to differentiate between different types of currents that it sees in the power system. All right, let's take a look at some other protective functions that other protective relays work with. We already mentioned under and over voltage. Under voltage causes the current to rise. Over voltage causes stress on the insulative properties of our system components. We have impedance relaying, mostly limited to transmission lines. We have directional overcurrent relay. We protect the generator core and the transformer core with a volts per hertz relay. Reverse power relays make sure that the power is flowing in the correct direction. We have loss of field relays that make sure that our synchronous generators have proper excitation so that they can continue to put out rated volts and amps. We have negative sequence relays that make sure that if the negative sequence voltage or current in the system exceeds setting, that we open the circuit breaker so that we don't have rotor damage on generators and motors. And then we have out of step, so that if two generators fall out of synchronization, we can tell whether we can smoothly get back into synchronization or if we have to trip off. And there are many others. I'm sitting here thinking of 81 frequency relays. So we've got relays that look at over frequency and under frequency and do load shedding. And the list goes on and on. The number will go from 1 all the way to 100 as far as protective device functions go. All right. Now, when we think about all of these protective functions, the whole idea here is that we can detect abnormal system conditions, that when we see these normal system conditions, that we can do something to mediate those abnormal conditions, and that once those conditions are mediated, we can bring the system back in to delivering power to the final load. So let's take a look at our relay operation in the power system and talk about what actually happens. So think about this. One of our 4 faults occur. If the fault occurs, the relay has to detect that type of fault or that type of abnormality, determine whether it needs to trip. If it determines that there's trip necessary, the relay operates and causes the circuit breaker to trip. Now, if the circuit breaker trips, then the fault is removed. Once the fault is removed, the relay can reset. Now, this is an important point. Think about this. Our relay resets by itself. Unlike a fuse that has to be replaced, when our relay resets, it doesn't have to be replaced. We have an operation, we don't have to go get a new relay. Once our relay resets, because the fault has been removed, we can then reclose the circuit breaker and return our system back to normal. All right, we've talked about a lot of things. We've talked about power system components, the actual physical devices. We've talked about the power delivery grid. We've talked about the type and number of relays. We've talked about what faults are, what's present under fault conditions, how our protective relay sees those conditions and takes the appropriate action. So in summary, here's what we're saying. Our protective relays are a critical component of a safe and reliable power delivery system. Protective relays cover system abnormal conditions from very simple, such as overcurrent and voltage protection, to extremely complex, such as impedance relays with communications over long distances. The types of protective relays, and these relays might all be found on the same bus. You might have mechanical relays, solid state relays, and numerical or microprocessor-based relays all on the same bus. If our relays are properly configured and maintained, they will provide system security and reliability. Thanks a lot for listening. We appreciate it.
Thank you, Dennis, for that presentation. We now would like to show you the suite of protective relay maintenance courses that ABO Training offers. You'll notice that we go from protective relay basic all the way through microprocessor relay testing, distribution and industrial, and also generation. You'll notice also that there are 4 certification courses within that suite, and we invite you to go to or visit adotraining.com to find out more information. We'd like for you to submit your questions now that Dennis has finished his presentation, and we'll answer those in a minute. But I wanted to remind everybody that our next webinar is scheduled for August the 15th, 1 p.m. to 2 p.m. Central Daylight Time, and it's part 3 of our electrical cable series with Mark Franks. The title of this presentation will be Fault Location, Testing, and Tracing. How do you avoid unplanned outages? Now we'll open up for some questions. Dennis, we've got quite a few questions that have come in. The first one, electromechanical or microprocessor relays, which are better for what grid condition?
So that's an excellent question. Probably better doesn't really enter into the equation here. So let me give you an example. The instantaneous unit on a mechanical relay actually operates faster than the instantaneous unit on a microprocessor-based relay. The reason that we're going to microprocessor-based relay isn't that the relay detects any better or operates any faster. It doesn't. But what it does do is gives us tons and tons and tons of data. And data is what every grid operator wants now. Think about what you get with a mechanical relay. Okay, with a mechanical relay, you get a $2.69 plastic target. That's the only indication of what went wrong in the system. Versus that same fault with a microprocessor-based relay, you get sinusoidal representation of the fault, you get a numerical representation of the fault, and you get a vectorial representation of the fault, including up to 16 cycles before and 8 cycles after. So really, the difference is data.
Thank you, Dennis. Ralph wants to know, why do negative sequence currents not cause damage to transformers while causing damage to generators and motors when they are constructed of the same material? Only that transformer is not rotated.
That's correct. Because we have a rotating field inside of our generators or motor, we produce under negative sequence conditions a twice-rated frequency current on the rotor and non-conductive metal of the rotor. The non-rotating transformer simply sees the negative sequence current as an elevated current. As an example, a large negative sequence fault would be 15% of the total current available in the system, and the transformer easily rides through that, or the conductor easily rides through that. But because we have a rotating magnetic field in our generator and motor, we see twice-rated frequency currents appear on the rotor and rotor non-conductive metals.
Dennis, Daniel wants to know, can an old fuse disconnect switch be retrofitted somehow to accept a protective relay control signal?
Probably not. That would be satisfactory for protective purposes.
Okay. Do test methods differ from electromechanical to microprocessor-based relays?
Personally, I think they should, but in reality, they don't differ that much, and here's why. We simply take the old electromechanical test procedures and apply them to our microprocessor-based relay. Okay? But I'll give you a quick example. In the mechanical world, I have an A-phase relay, I have a B-phase relay, and I have a C-phase relay. Each one of those relays are separate and independent relays and have to be tested individually. In the microprocessor-based world, that's simply not true. It's all math. So if the processor processes the A-phase fault properly, I don't need to look at the B-phase or C-phase conditions on the microprocessor-based relay because it's all the same circuit. So separate circuits in the mechanical world, same circuit in the microprocessor-based world, but presently most of us test our microprocessor-based relays almost identical with the way we did mechanical relays, simply because that's what is available as far as test procedures go.
Dennis, what would cause a ratio mismatch between a high and low side of the transformer?
Okay, the mismatch is pretty simple. The transformer has a specific ratio, and the problem is that ratio is not always a whole number. Okay, it's not always a whole number, but CT ratios are whole numbers. So if I have, as an example, a transformer that has a ratio of 1 to 2.5, there's no CT ratio that will match that. So we have a ratio mismatch. Plus, if it's a delta Y or Y delta transformer, we also have a 30-degree phase shift that affects the currents. So CT ratio mismatch, where the CT ratios are mismatched with the transformer ratio, and a phase shift across the high voltage and low voltage winding cause ratio mismatches, but all of our differential relays that are designed to protect transformers can take that ratio mismatch into consideration and properly match the currents in the relay. We can't match them at the CTs, but we can match them in the relay.
Dennis, what determines which function should be used in my system?
Okay, what we have to determine is number one, what are you trying to protect? So if you have a simple bus, probably overcurrent or directional overcurrent relays are sufficient. If you have a generator connected to that same bus, now you've got to have generator protective relays. If you have a transformer on that same bus, now you have to add not only the overcurrent relays to protect the bus and the generator, but now you've got to have transformer differential protective relays. So it really depends on the equipment. Remember, all the equipment has to be protected. It would be ineffective to try to protect your generator with standard overcurrent relays. It'd be nearly impossible to protect a transformer with just a standard overcurrent relay. So depending on the equipment, depends on the type of relays that you have to use.
Dennis, how do relays operate in an FLISR type scenario?
I'm assuming FLISR, are we talking about frequency load shedding? I'm not sure, but if we're talking about frequency load shedding and reclosing here, we're simply saying that we use the protective relay to shed load until the generator can handle the load that it sees, and then as the system is restored, we can reclose load back into the generator and restore system operation. I may be missing what FLISR stands for there. I apologize if I didn't understand that question.
Dennis, after the relay operates due to a system fault and resets, should the relay be retested to verify proper operation, or just wait until the next maintenance cycle?
Okay, great question. And really, it's dependent a lot on what the engineering department needs. I know back a few years ago when I was testing a lot of relays, every time we had a relay operation, the system engineer wanted to just go out and retest the relay. Even though we knew the relay had operated properly and that there was an actual fault on the line, he always wanted the relay retested. I'm not sure I agree with that. If in today's world, we generally know if we truly have a fault. If the relay operated properly, what you should do is, if it's mechanical, you should go out and retest the target. But I see no need to test the relay unless you suspect that there's a relay problem. They're designed to see faults over and over and over and operate properly.
Dennis, who's in charge of the inner grid protected relays?
Okay, if we're talking about the inner tie between, as an example, utilities, that's the regional dispatch centers. So back in the day, what used to happen was that a utility would say, hey, if I'm not having any problems and you are having problems, I'm going to disconnect you. But now the grid operators do the under frequency load shedding and the under voltage load shedding, and they may shut a perfectly healthy utility off line in order to preserve the grid. So again, the interties are controlled, especially on large generating and transmission systems. Those intertie substations are controlled by the grid operators and not by the individual utilities.
Okay, thank you, Dennis. What is the percentage of differential relay?
Okay, the percentage, if we're talking about the percent slope, which is usually when we talk about differential relays, we're talking about this percent slope, is the allowable current difference between the two CTs, one on each side of the transformer or one on each side of the generator. How much difference will you allow before you declare that the difference is greater than normal and issue a trip to the generator or transformer circuit breakers? So again, that percentage is the percentage of allowable difference between the two measured currents coming into the transformer or the generator.
Dennis, what is the recommended frequency for testing for solid-state relays and for numerical relays?
All right. In this case, I am going to defer to FERC and NERC. Here's what they say. Microprocessor-based relays should be checked to make sure that the settings are correct and that the relay is metering properly every 6 years. Mechanical relays by FERC and NERC standards have to be tested every 6 years, but they have to be injected with simulated inputs to make sure that they operate properly. So mechanical relays require testing of all of the elements in the relay. Microprocessor-based relays presently require only that you go in and do a meter test and then make sure that the settings are correct. Now, don't get fooled here. Your company may have specific maintenance intervals, but it has been the trend over the last few years to stretch those maintenance intervals out. So instead of beginning with relay A and going to Z and then starting with A again, many companies say, hey, we're only going to test our relays every 5 years. And there's probably good reasons for that. So I'm going to say the maximum you should go is 6 years, and then your engineering staff needs to make a decision on how frequently you do it outside of that 6-year limitation.
Dennis, here's a fairly complicated question. We'll see if we can get this in the 30 seconds. With the expansion of renewable power sources, what are the challenges that Relay World faces, taking into account that most actual relays act unidirectional and the power flow could change directions with these new power sources? Absolutely right. So as an example, when we're looking at turbine strings on wind turbines, okay, we definitely have to have directional overcurrent relays that can sense the direction of power flow and know whether the power is flowing out to the grid or for some reason flowing back into the turbine. So things like wind turbines, things like complex switching systems all require more and more complex relaying, and it's a challenge for engineers as we go along. Our systems are not getting easier. They're getting more complex, and so we have to have more complex devices and more complex learning processes. Dennis, Jason wants to know, do you feel 21 distant relays are accurate and effective? The answer is twofold. If we're talking about mechanical distance relays, they work. They are accurate and effective. However, microprocessor-based relays are much more accurate and much more effective, and many more things can be done with the impedance functions on a microprocessor-based relay versus a mechanical relay. Dennis, we're almost out of time, but for those attending, we're going to stay for about 5 more minutes because we've got probably more questions that we're going to get to the answer today. So let's just go for another 5 minutes here. Question came in. Do the backup relays have to be the same type as the primary relays? Most engineering schools are teaching that they should not be the same, because if I have 2 identical relays, and this is especially true in the microprocessor-based world,
and there is some kind of logical error in those relays, then both relays will react improperly to the same condition. So generally we see a manufacturer, as an example, General Electric as our primary, and perhaps Schweitzer or someone else as the backup, because the logic functions and relay types are completely different, and therefore a problem in one won't be necessarily reflected in the other. Now in the mechanical world, if you have backup relays, they can be the same because our mechanical relays have been proven over and over and over again.
Dennis, another question has come in. The input to bus, a differential relay, was shown to be of several equipment CT inputs on a bus. How does the relay distinguish a differential event with the bulk summation of current?
Okay, so we're talking about bus differential relay. Here's what we have: two parts to this. One part is the in-feed into the bus and the current exiting the bus. So it's very simple. If the current going into the bus does not match the current going out of the bus, the question is, where is that current going? That current's probably going to ground. So at the relay, we're going to see a difference in current. Under normal conditions, no current enters the relay because the current on the load side and the current on the incoming side are equally matched and 180 degrees out of phase. But if there's a grounding problem on the bus or a phase-to-phase fault, the two currents will not match. Therefore, we will have a difference current entering the relay, and the relay will trip if that difference is greater than setting.
Dennis, what is the current measurement accuracy for solid-state relays compared to numerical relays?
I'm going to be, because we're taking an analog signal in a solid-state relay and converting it to a DC signal, it's not as accurate as converting the analog signal directly to a digital signal. But we're talking about small percentage errors here. A solid-state relay might be 3% accurate, and a microprocessor-based relay would be 2% accurate. Don't get involved in that, because remember, under fault conditions, the CT itself is only 10% accurate. So don't quibble about a half percentage or percentage difference between a solid-state relay and a microprocessor-based relay. They've been proven for many years. They work just fine, and it's an engineering choice.
Dennis, how does a frequency relay work? Does it sense a difference in the frequency only?
Okay. Generally speaking, out in the power system, when we have a frequency problem, there's also a drop or rise in the voltage. However, the frequency relay is tuned to look at a specific frequency only, and the only role the voltage plays is in what we call under voltage cutoff. So until the voltage drops below a specific level, the relay is only looking at just the frequency and is set to a specific value. As an example, 59.5 hertz for under frequency, 60.5 hertz for over frequency, and we really don't care what the voltage is until we hit an under voltage cutoff level that cuts off frequency measurements because it's inaccurate below a certain voltage level.
Okay, thank you, Dennis. We have enough questions to last for probably another 30 or 40 minutes. So to everybody that submitted questions, we will send an email answer to these questions. And we want to basically thank you for attending today. And thank you, Dennis, for your expertise. You can again go to adotraining.com and you can see a host of relay courses that we offer with knowledgeable people like Dennis conducting the instruction. We hope to see you again for the next webinar. And remember, we will send you an email with the NETA CTDs and also the professional hour credit, how to achieve those. Thank you for joining us, and we'll see you at our next webinar, August the 15th, 1 to 2 p.m. Central Daylight Time. Thank you again.